Hello everyone. Good evening, good morning. My name is ParinShah and I work as an embedded AI research engineer at AI Shield. Thank you for selecting our case study and giving us an opportunity to present our work. TinyML devices are vulnerable, a study of attack kill chain for TinyML devices. The paper's co-authors are Yuvraj Govindarajulu, Pawan Kulkarni and Manoj Kumar Parmar. Today, in this presentation, we'll discuss how AI systems deployed on resource-constrained embedded devices are vulnerable to adversarial attacks, and why traditional mitigation strategies are insufficient to secure AI systems developed on embedded hardware or tiny devices. Following will be the outline of today's presentation, starting with an introduction of TinyML, where we'll see the growth of AI and AI on tiny devices. Moving forward, we'll have a look into what are the security risks in tiny devices. Following to which, we'll explore the Mitre Atlas kill chain on how an attacker can attack the model and can steal the critical information. Next, we'll explore adversarial attacks and the different kinds of attacks based on the knowledge of the model an adversary has. Finally, we'll conclude with mitigation strategies to secure AI systems deployed on embedded devices across various applications. TinyML, the power of AI/ML on the tiny devices, which means deploying a machine learning model on a embedded devices or a microcontrollers with minimum computational resources presents challenges due to constraint on power consumptions, memory, and processing capabilities. This necessitates and the design and optimization of machine learning algorithms to operate within these limitations, enabling intelligent functions on diverse edge devices. However, deploying such intelligent systems in sensitive environments like healthcare and industrial control raises significant security concerns. These systems often handle sensitive data and controls critical infrastructures, and this resource constraint and limited computational power often makes them vulnerable to adversarial attacks. Here, we will have a look into what are the security risks a tiny ML device possesses. Often, the edge devices are deployed on a remote location, giving easy physical access to any adversary. Adversary with direct access can manipulate the hardware component, potentially altering the device behavior or even stealing sensitive data stored locally. Since these models run directly on the devices, attackers with physical access can potentially steal the intellectual property from the model. Since TinyML devices are also communicated over unsecured network, due to which an attacker can intercept the data being transmitted. This data could include sensor readings, control signals, or even the model itself. Due to limited resources, it lacks the processing power and memory needed for robust security measures like encryption and secure boost. Because of the limited resources, often simplified softwares are run on these devices, making them more susceptible to attacks, and vulnerabilities in the softwares are impacted. Mitre Atlas, that stands for an adversarial threat landscape for AI systems. It essentially serves as a comprehensive database or knowledge base outlining how attackers can target AI systems. This includes detailing various tactics and techniques that attackers might use, as well as providing real-world case studies of attacks on AI systems. It serves as a roadmap to enhance AI security. By understanding the tactics and techniques that attackers might employ, AI security professionals can better anticipate and prevent potential attacks on AI systems. When Mitre Atlas kill chain is applied to TinyML low power devices, potential vulnerabilities and attack stages for small scale AI models operating on constrained hardware are highlighted. These devices, commonly found in IoT and edge computing, are susceptible to reconnaissance and exploitations due to limited resources and security controls. In TinyML devices, attackers can manipulate sensor inputs to influence model outcome, thus compromising the device reliability. The kill chain emphasizes the significance of securing data pathways, implementing robust anomaly detection, and maintaining secure device firmware to mitigate risk. Here, the highlighted part shows how an attacker can follow this process and can extract the sensitive data or intellectual property from the model or the model in itself. In the context of an attack kill chain, according to Mitre Atlas, this demonstrates how an attacker can compromise functionality of a tiny devices. Initially, the adversary conducts reconnaissance to identify the target AI model and analyze their architecture, framework, and deployment specifics, aiming to exploit vulnerabilities or intercept communication to gain unauthorized access. Subsequently, employing a potent attack like model extraction, which focuses on reverse engineering and replicating the AI model, the adversary reconstructs the AI model. Finally, leveraging the preferred model, the adversary can generate adversarial samples from a powerful system to compromise the low power devices. Here, we will go through the security threats that an AI/ML models are vulnerable to. Security threats in AI covers various risks and vulnerabilities that can emerge during AI technology development, deployment, and its usage. These threats affect the reliability of AI systems and their operational environment. Based on the extent of attackers' knowledge regarding the targeted AI model or systems, adversarial attacks can be classified or categorized into three types. First, no knowledge or black box, minimum knowledge or gray box, complete knowledge or white box. In black box or no knowledge, the attackers may attackers will have a zero knowledge of the internal working of the system. In minimum knowledge, it involves exploiting vulnerabilities in AI systems where the attacker has partial knowledge of the internal workings of the system. In white box or complete knowledge, the adversary has the complete knowledge of the targeted model, including the weights, parameters, and sometimes the labeled training datasets. Following are the security threats that to which an AI models are vulnerable to. At different stage of AI lifeline, adversaries can attack the AI models at various levels of maturity, like data poisoning that occurs during data preparation where adversaries inject malicious data to influence models' training processes. Model extraction that involves replicating important information from the deployed model, potentially leading to intellectual property theft or unauthorized model replication. Model evasion that involves manipulating the manipulating the model's input data in a subtle manner, causing it to make incorrect predictions while remaining imperceptible to humans. And membership inference, in which the attacker's aim is to determine whether specific data points belongs to the training data of a particular ML model. This essentially reveals whether someone's information was used to train the model. Here, in this research, we have explored two kinds of adversarial attacks. That is, one is model extraction attack and model evasion attack. Model extraction attack. It is designed to duplicate the functionality or steal the functionality of the trained model, and it aims to reconstruct a local copy of the model. The concept of model extraction is shown in the following figure. Consider an example where a company has trained an AI model using a proprietary dataset. An adversary can query X, this trained model to obtain a prediction Y on input features, vectors, and therefore construct a learned label dataset. Attackers can then train a replication model on this learned label dataset to approximate the trained model without prior knowledge about these parameters. A model extraction attack is termed as black box if the adversary replicates the model using synthetic inputs without prior knowledge of the domain or model parameters such as architectures and weight. Here, we have performed the model extraction attack on gesture recognition dataset that comprises of three distinct gestures, that is ring, wing, and slope. During our experiment, we were able to successfully replicate the original model's information and functionalities, achieving a success rate of 75%. This success rate indicates the percentage of original model's functionality that were replicated. Here in the table, we have compared the results on host and on the ESP32 device. As we can see that no matter if the AI model is deployed on the host or a tiny embedded device like ESP32, we were successfully able to replicate the original model's functionalities. Following figure shows the attack queries that were used to train the surrogate model, on which we achieved an accuracy of 69.23%. Now, model evasion attack. Evasion attack involves the manipulation of input data to mislead an AI model's prediction or classification, in this adversaries introduce small perturbations to the input features by applying incremental change in the direction of the gradient of the loss function for each feature. As we are accessing the gradients, it's a white box attack because we have the complete knowledge of the model. These perturbations, which often imperceptible to humans, can cause significant alterations in the model's output. By impacting the model sensitivity to these perturbations, attackers can induce mispredictions or misclassifications. That raises a critical concern about the robustness of the AI system, particularly in a safety critical domain like autonomous driving or healthcare. Here, in the model evasion results, we can see how by adding up perturbations in increasing amount, we were able to increase the efficacy of the original model. That means the decrease in accuracy. For epsilon zero point 0.9, we were able to misclassify 95.76% of the original class. That means the model was able to misclassify 95.76 of the times. Here, from the current experiments, we can see that AI models deployed on tiny devices are vulnerable to adversarial attacks. This adversarial attack poses a serious threat by compromising data integrity. Attackers manipulate sensors data with subtle alteration that are imperceptible to the human eyes but can fool the AI systems. This adversarial data leads the AI to make incorrect decisions, disrupting critical operations in various applications. In safety critical areas like autonomous vehicle or medical diagnostic, these attacks can create serious problems. Following are the mitigation strategies to safeguard the AI systems. 1. Robust training or creating a detection mechanism. Instead of training the model only on the clean, normal data, robust training involves incorporating data that simulates potential attack. Through robust training, the model becomes more resilient to adversarial attacks, as it learns to distinguish between legitimate and malicious inputs more effectively. While robust training enhances the model's security against attack, it may also result in slight reduction in the accuracy when processing normal, clean data. This trade-off occurs because the model is trained to be more conservative in its prediction, which can sometimes lead to false alarm or misclassification on regular dataset. In detection mechanism, it is designed to differentiate between regular expected data and abnormal or potential malicious data. This is crucial for identifying and flagging potential threats or attacks. This mechanism typically employs an ML model or AI model to analyze various features or attributes of the input data to determine whether it's an expected data or the malicious data. This feature could encompass patterns, behaviors, or statistical properties. Through the analysis of extracted features, an AI/ML model can classify each data point as either normal or anomalous. By implementing these strategies, we can shield and secure our AI systems and can make it trustworthy for the users. Thank you. We at AI Shield are committed to secure the AI systems of the world.